equivalence relations, then there are some things that I need to inform you of concerning finite sets and infinity and things like that. But in that section, the proofs are sort of very ad hoc, meaning they kind of only work for, they're not very general in nature, whereas most of what we do in here, the proofs are things that you may use in some other area. Now, if you do go into some field like graph theory or discrete math, then some of those techniques will be useful for you. That just depends on what we do. We don't really do much graph theory here in the math department, although it is applied in many situations. But for example, in the computer science department, there's a lot of graph theory that goes on with circuit board design and those kinds of things. All right, so it is important. It's just a lot of the proofs are not going to be used by you in your later classes, or those kinds of proofs. Now, equivalence relations. I got to tell them to not get some of these. I think this is the one I brought down. Equivalence relations. Okay, that's a brand new pen, I thought. I know the red works. This is an extremely important concept that you'll see all the time, almost immediately in your first algebra course, for example. I mean your first real algebra course. So actually, this is a little story, of some of the things that happen to you when you're a math graduate student. So when I was a graduate student at the University of Maryland, I was taking graduate algebra, but the title of the book that was used for that class was called Basic Algebra 1. So I had to walk around on campus carrying this book. It didn't have any fancy pictures on it or anything, right? So people probably thought it was kind of a weird algebra book. But yeah, so I had to have this book called Basic Algebra 1. Actually, it was not a very pleasant book. It was full of typos, which made it really, really, really exciting to try to understand it. All right. But you will see these in pretty much in all fields of mathematics. They come in a big way. And so I'm going to use tilde. That's the way mathematicians call it. I had a physics professor who called that twiddle. Okay, your choice. It's like the difference between phi and phi, right? But this is a notation we'll use when we have an equivalence relation as opposed to R, which we use for sort of a general relation. You will also see the following notation, and in fact we'll use that a little bit later for equivalence. The main thing you will not see is equals in general. You will also see this symbol used for equivalence relations. Okay, so last time we got the definition, right? And it will take you some time to get used to this definition and what it means, especially when we get into equivalence classes. And let's say on X is called an equivalence relation. If, okay, so who remembers?
Reflexive.
Okay, number one, reflexive. Okay, so somebody else says what it means. You're off the hook. Reflect. And I don't mean reflect on it. I mean, what does reflection do?
X or X for all X.
Yeah, so and now we're using tilde, right? Everything is related to itself. Okay, second one.
Symmetric.
Symmetric, which means what?
If X tilde Y, then Y tilde X.
Yeah, and you can read this as equivalent to also. If X is equivalent to Y, of course that's a little premature since we haven't actually, these are what you're verifying, but anyway, if X is related to Y, then Y is related to X. Now, a common thing that I see happen in this class with people who aren't working with the definition enough is I will see this expressed as X related to Y and Y is related to X. Okay, now some of the red is useful, okay? That's not what it means. And you may think, well, how would anybody get that mixed up? Well, believe me, it happens more frequently than you might think, okay? This is an if-then statement. So when you're proving this, you assume x is related to y, and then you find a way to prove, using the definition of the relation, that y is related to x. Okay, and the last one? This one you already heard, right? Back when we discussed ordering. If x is related to y, and y is related to z, then x is related to z. And again, the symmetric law allows you to mix this up a little bit, okay? So we'll often just use the symmetric law without actually saying anything about it. And just, you know, if you got x related to y, well, you might as well just say y related to x if you need it. Okay, so there are lots of variations on this theme, right? You could change this to y related to x without any problem, right? Because of the symmetric law. If you have an equivalence relation, if you have symmetric. If you don't have symmetric, then all bets are off there in terms of changing the ordering. Okay? So just keep that in mind. Now, as it turns out, it's a lot easier to find relations that are not equivalence relations than ones that are. Okay, so pretty much any relation you just write down, chances are it's not going to be an equivalence relation. And so a lot of your exercises at this point will be devoted to checking each of these properties. And you know, if they're not, if one of them is not true, then it's not an equivalence relation. Okay, so think about that. If the question asks you, is this an equivalence relation, how do you disprove it?
Find an example where one of them is not.
Yes, you find a concrete example where one of them doesn't work. And then you are done, okay? You don't need to check the other ones. The other ones could even be true, or they could not be true. Who cares, right? At least if that's the question. If the question is it an equivalence relation, you know, if you're doing this on the test, the answer is, if it's no, find an example to show that that one condition is not, you know, correct, and then you're finished with the problem. Okay? Be lazy about it. Don't do any more than you have to, especially on the test. So let's consider one more example of a relation. This is also not going to be an equivalence relation for sets A and B. By the way, notice I'm not saying we're going to have a relation on the set of all sets, because then that gets into scary territory. So we'll just say for sets A and B, we define A equivalent to B to mean there is a bijection. Oh, sorry, I want to do that one a little bit later. X related to B to mean A intersect B not equal to the empty set. Or you could do equal to the empty set. I think that's what's done in the text. It doesn't matter. The arguments are very similar, except for the first case. Okay, so is it reflexive? So is any set related to itself? I'm hearing a yes. So this is tweaked slightly from the text. Is a set related to itself or not? I heard a yes. Why are you saying yes?
Because it's a set, and so it's like every term in the set.
So the question is, if you pick up a set, is this intersection of the set with itself non-empty?
That would be always true.
Well, that's what Sarah's saying. Is it always true?
Yes.
Unless the set is an empty set.
Aha. What if A is the empty set? Okay, all you need is one example, right? No. So if A equals the empty set, A intersect A equals the empty set. So it's not reflexive. What about symmetric? So what would be my opening line to prove or think about what it means to be symmetric. You have to pick up A and B, and their intersection is not equal to the empty set. Then what would you have to check? Now everybody's scared, right? Because the first one seemed obvious and half the class. What's that?
Does B intersect A not equal to the empty set? Would that be?
Yeah, that's what you need to check. Well, is that true? Now everybody's spooked, right? It's like when you're out trout fishing, right? You let yourself be seen and then everybody goes and hides, right? And nobody, okay, so. Well, what about the empty set? Is that what you're worried about? What is the empty set related to? What sets is the empty set related to? Just the empty set, okay? Anyway, this is true, right? Because if some A intersect B is the same as B intersect A, right? So if A intersect B not equal to the empty set, then B intersect A is not equal to the empty set, right? End of story. How about transitive? If A intersect B is not empty, excuse me, and B intersect C is not empty, does A intersect C have to be not empty? No? Okay. Counterexample? Got to tell me 3 sets, A, B, and C.
A is 1, 2.
So A equals 1, 2.
B equals 2, 3.
Yep.
And C equals 3, 4. Or maybe I'm thinking of this one.
Maybe, what if C equals,
Okay, so first of all, A is related to B, right?
Yeah.
Okay, what did you say?
what if C is 1, 1, 3?
Well, what we want is for A intersect C, if we're going to do a counterexample, to be empty.
So
So
that works.
C is 3, 4.
Right?
3, 4 does work, yep. Okay, because A intersect B is equal to 2, which is not empty, and B intersect C equals 3, which is not empty, but A intersect C is empty. So the answer is no. By the way, what if we changed it to A intersect B equal the empty set? Does that change anything? I won't go through the details. Does it change reflexive? I've got one person nodding. You guys you're going to get more and more scared, right? Okay.
That's a no.
Still no. Right? Because in that case, if A is not empty, then the intersection with itself is itself, which is not empty. So either way, you're in trouble on the reflexive law. And then you can do something similar for the transitive law. And, okay? So it doesn't change things very much. That's the example that's done in the text. Okay, so that brings us to equivalence classes. Let X be a set with equivalence relation tilde. Okay, so in this case, we are assuming that we have an equivalence relation. If we don't have an equivalence relation, that is, if any one of these 3 things fails, all bets are off. The definition we're making here doesn't have the kind of properties that we want it to have. All right, and it does have some extremely useful properties, as we'll see. So we're assuming that it's already an equivalence relation. You might have to prove that in some specific case, but once you know it's an equivalence relation, then you can do the following. Okay, so for any x, an element of x, we define the equivalence class of x as, okay, and the traditional notation is x bar, okay, and it's still a little x, but even though it's a little x, x bar is a set. Okay, so this is the set of all y, an element of x, such that x is related to y. So the equivalence class of this little x takes everything in x and it puts it in this set if it's actually equivalent to x. Okay, so again, this is a set, and that's going to be the most confusing part of this, right? But it actually should seem like a very natural concept, so let's look into it a little bit more. First thing to note, what are you guaranteed to have in x?